Power consumption is measured in kilowatts. For the 240 volts heater, power equals voltage times current, so 240 volts times 10 amps times 2 for the two legs equals 4.8 kilowatts. For the 120 volts heater, power equals voltage times current, so 120 volts times 10 amps equals 1.2 kilowatts. Therefore, the 240 volts heater consumes more power, 4.8 kilowatts, than the 120 volts heater, which uses 1.2 kilowatts. Your electricity bill is based on the amount of energy you consume, which is measured in kilowatt hours. For the same amount of time, the 240 volts heater uses 4.8 kilowatts times the time in hours, which equals the kilowatt hours, while the 120 volts heater uses 1.2 kilowatts times the time in hours, which equals the kilowatt hours. Since the 240 volts heater consumes more power, it will use more kilowatt hours, and you will get a higher charge from the power plant if it runs continuously for the same period of time as the 120 volts heater. The number of legs does not affect the amount of power consumed. However, it does affect the wiring configuration and the circuit breaker requirements. The 240 volts heater requires a dedicated circuit with a 2-pole circuit breaker. The 120 volts heater can share a circuit with other appliances, as long as the circuit breaker is rated for the total current draw. To further understand the power consumption, let's delve into the underlying principles. Power, measured in watts or kilowatts, is the rate at which electrical energy is transferred by an electrical circuit. It's the product of voltage, which is the electrical potential difference, and current, which is the flow of electrical charge. In direct current, or DC, circuits, the power calculation is straightforward. It's simply voltage multiplied by current, or P equals V times I, where P is power, V is voltage, and I is current. However, in alternating current, or AC, circuits, the calculation can be a bit more complex, especially when dealing with reactive loads. Reactive loads, such as inductors and capacitors, introduce a phase shift between voltage and current, which reduces the amount of real power delivered to the load. The power factor is a measure of how effectively electrical power is being used. It's the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. A power factor of 1 indicates that all the power supplied to the load is being used to perform work. A power factor less than 1 indicates that some of the power is being wasted due to reactive components in the load. In the case of the electric heaters, they are resistive loads, meaning they primarily convert electrical energy into heat. Resistive loads have a power factor close to 1, so the power calculation is essentially the same as in a DC circuit. Now, let's consider the implications of using different voltages. A higher voltage allows for the transmission of the same amount of power with a lower current. This is because power equals voltage times current. If you increase the voltage, you can decrease the current while maintaining the same power level. This is advantageous because low current reduces resistive losses in the wiring. These losses, often referred to as I²R losses, are proportional to the square of the current and the resistance of the wire. By reducing the current, you significantly reduce these losses, which improves the efficiency of the electrical system. That's why high voltage transmission lines are used to transmit electricity over long distances. By transmitting electricity at very high voltages, power companies can minimize losses during transmission. When the electricity reaches your home, it's stepped down to lower voltages such as 240 volts and 120 volts for safe use in appliances and lighting. The 240 volt circuits are typically used for high power appliances such as electric ranges, clothes dryers, and water heaters. These appliances require a lot of power to operate, and using 240 volts allows them to draw less current, which reduces the size of the wiring and circuit breakers required. The 120 volt circuits are typically used for lower power appliances and lighting. These circuits are more common and are used for most household electrical needs. Now, let's discuss the impact of using 2 legs versus 1 leg. In a 240 volt circuit, 2 hot wires, each carrying 120 volts with respect to neutral, are used to provide the 240 volts potential difference. The load is connected between these two hot wires. This configuration is commonly used in North America. In other parts of the world, different voltage standards and wiring configurations may be used. The advantage of using two legs is that it allows for a more efficient distribution of power. By using two legs, the current is split between the two wires, which reduces the current in each wire. This reduces resistive losses and improves the overall efficiency of the circuit. In the case of the 240 volts heater, using two legs allows it to draw 10 amps on each leg, which is equivalent to drawing 20 amps on a single leg. By splitting the current between two legs, the current in each wire is reduced, which reduces resistive losses. The 120 volts heater, on the other hand, only uses one leg. This means that all the current flows through a single wire. This can result in higher resistive losses, especially if the wiring is not adequately sized. In general, it's always best to use the appropriate voltage and wiring configuration for the load. Using a higher voltage and a two-leg configuration can improve efficiency and reduce resistive losses. Now let's talk about the circuit breaker requirements. The circuit breaker is a safety device that protects the electrical circuit from overcurrents. It's designed to trip and interrupt the circuit if the current exceeds a certain level. The circuit breaker rating is determined by the ampacity of the wiring. The ampacity of a wire is the maximum amount of current that it can safely carry without overheating. The National Electrical Code, or NEC, provides guidelines for determining the ampacity of different types of wires. The NEC also specifies the minimum size of wiring and circuit breakers for different types of loads. In the case of the 240 volts heater, it requires a dedicated circuit with a two-pole circuit breaker. A dedicated circuit means that the heater is the only load connected to that circuit. This is to prevent overloading the circuit. A two-pole circuit breaker is required because the heater is connected to two hot wires. The circuit breaker must be rated for the total current draw of the heater, which is 10 amps on each leg, or 20 amps total. In the case of the 120 volts heater, it can share a circuit with other appliances, as long as the circuit breaker is rated for the total current draw. This means that the circuit breaker must be rated for the current draw of the heater plus the current draw of any other appliances connected to the circuit. It's important to note that you should never overload a circuit. Overloading a circuit can cause the wiring to overheat, which can lead to a fire. If you're not sure how to determine the correct size of wiring and circuit breakers, it's always best to consult with a qualified electrician. Now let's consider the cost of operating the two heaters. As we discussed earlier, the 240 volts heater consumes more power than the 120 volts heater. This means that it will use more kilowatt hours and you will get a high charge from the power plant if it runs continuously for the same period of time. The cost of operating an electric heater depends on several factors, including the power consumption of the heater, the cost of electricity, and the amount of time that the heater is used. The power consumption of the heater is determined by its wattage. The higher the wattage, the more power the heater consumes. The cost of electricity varies depending on where you live. In some areas, electricity is relatively inexpensive. In other areas, it can be quite expensive. The amount of time that the heater is used also affects the cost of operation. The longer the heater is used, the more energy it consumes and the higher the cost. To estimate the cost of operating an electric heater, you can use the following formula: cost equals power in kilowatts times time in hours times cost of electricity per kilowatt hour. For example, if you have a 1.5 kilowatt heater and you use it for 8 hours a day and the cost of electricity is 10 cents per kilowatt hour, the cost of operating the heater would be 1.5 kilowatts times 8 hours times 10 cents per kilowatt hour, which equals $1.20 per day. To reduce the cost of operating an electric heater, you can take a few steps. Firstly, you can use the heater only when needed. Instead of leaving the heater on all the time, turn it off when you leave the room. Secondly, you can lower the thermostat setting. The lower the thermostat setting, the less energy the heater will consume. Thirdly, you can insulate your home properly. Proper insulation can help to keep your home warm in the winter and cool in the summer, which can reduce the amount of energy needed to heat and cool your home. Fourthly, you can use a programmable thermostat. A programmable thermostat allows you to set different temperatures for different times of the day. This can help you to save energy by automatically lowering the temperature when you're not home or when you're sleeping. In summary, the 240 volts heater consumes more power than the 120 volts heater. This means that it will use more kilowatt hours and you will get a higher charge from the power plant if it runs continuously for the same period of time. The number of legs does not affect the amount of power consumed. However, it does affect the wiring configuration and the circuit breaker requirements. The 240 volts heater requires a dedicated circuit with a 2-pole circuit breaker. The 120 volts heater can share a circuit with other appliances, as long as the circuit breaker is rated for the total current draw. By understanding these principles, you can make informed decisions about which type of heater to use and how to operate it efficiently. Remember to always consult with a qualified electrician if you have any questions about electrical wiring or safety. Also consider energy-efficient models of electric heaters, which may have features like automatic shut-off timers and more accurate thermostats to help you conserve energy. And consider if an electric heater is the best heating solution for you. Depending on the climate and usage patterns, other heating systems such as natural gas, heat pumps, or even passive solar heating may provide more cost-effective solutions. If you are building a new home or significantly renovating an existing one, consider a whole house energy audit to identify the best opportunities for energy savings and improvements to home comfort. A professional energy auditor can assess your home's insulation levels, air infiltration rates, and heating and cooling system efficiency to make recommendations tailored to your specific situation. Furthermore, explore renewable energy options such as solar panels, which can offset your electricity consumption and reduce your reliance on the power grid. Government incentives and rebates are often available to help offset the upfront costs of renewable energy systems. Another factor to consider is the placement of the electric heater within the room. Placing the heater near a window or door can result in heat loss, as the heat will escape to the outside. It's best to place the heater in a central location in the room, away from windows and doors. You should also avoid placing the heater near flammable materials, such as curtains or furniture. The heat from the heater could ignite these materials and cause a fire. Always follow the manufacturer's instructions for safe operation of the electric heater. This includes keeping the heater clean and free of dust and debris. Dust and debris can accumulate in the heater and cause it to overheat. You should also inspect the heater regularly for any signs of damage. If you notice any damage, such as frayed wires or cracked housing, you should stop using the heater and have it repaired by a qualified technician. When using an extension cord with an electric heater, make sure that the extension cord is rated for the wattage of the heater. Using an extension cord that is not rated for the wattage of the heater can cause the extension cord to overheat and create a fire hazard. It's also important to avoid overloading electrical outlets. Overloading an electrical outlet can cause the outlet to overheat and create a fire hazard. If you need to plug multiple appliances into the same outlet, use a power strip with a surge protector. A surge protector can protect your appliances from power surges, which can damage them. Also, be aware that some electric heaters have safety features, such as step-over switches, that automatically shut off the heater if it is knocked over. This can help to prevent fires and other accidents. Familiarize yourself with the safety features of your electric heater and make sure that they are functioning properly. Finally, remember that electricity can be dangerous. Always take precautions when working with electricity and follow all safety guidelines. If you're not comfortable working with electricity, it's best to consult with a qualified electrician. By following these guidelines, you can safely and efficiently use electric heaters to heat your home.